All right, so we're going to take a look at an example circuit, second order circuit, and try to figure out the response. So in this particular case, the circuit I have is shown right here, and I'm going to change real quick. I'm going to call this guy IL and that guy VC. And I want to find VC of t for t greater than 0, assuming that that switch right there has been closed for a long time before t equal to 0. So in other words, we're going to try to follow this sort of step-by-step process to try to solve the differential equation here. All right, and I'm going to define a couple of things as I go through this, right? I'm going to call this guy R1, call this guy L, call this R2, and call that C. All right, when I write the differential equations, I'm going to write them in those terms, okay? And we'll come back and use those numbers eventually. All right, the first step for me is to basically kind of always sort of go through this circuit and try to figure out what I need to be able to calculate the initial conditions. Okay, so for me, step one is to find VC of 0 minus and IL of 0 minus. And the reason I start with those two in particular, right, is because I know that VC of 0 minus always has to equal VC of 0 plus, and IL of 0 minus always has to equal IL of 0 plus. Okay, that will help me to get part of what I need for my initial conditions. Okay, all right. So to do that, I need to look at this circuit, and I basically need to look at the circuit before that switch is closed. Okay, so we've been told in the problem statement that the switch has been open for a long time before t equal to 0. So that means basically at t equal to 0 minus, the circuit looks like this. I've got a 12 volt source. Okay. Now the switch is open. If at t0 minus that switch has been open for a really long time before t0 minus, that tells us that the inductor basically looks like a short circuit at that point, because in steady state an inductor looks like a short and a capacitor looks like an open. So that tells us that we have 4 ohms here. Two ohms here. Oops. I'm wrong when I put that 2 ohms in there, right? Because actually that switch was open. All right, so let me get rid of that. All right, and so my circuit actually looks like this. Okay, where I'm just looking at the capacitor voltage right there. So by straight up KVL on this particular guy, it's pretty easy for me to see that voltage, if I have an open circuit like this, there's no current flowing through that loop, so this voltage better be 12 volts. Right? In other words, there can't be any voltage drop across that 4 ohm resistor because the current is 0. So I can see right away that VC of 0 minus is equal to 12, right? Which also, I guess the current through this circuit is actually IL of 0 minus. So right now I can see that VC of 0 minus, which is equal to VC of 0 plus always, is equal to, in this case, 12 volts. And IL of 0 minus, which always has to equal IL of 0 plus, is equal to, in this case, 0 amps. Okay? So that gives me one of the initial conditions that I'm going to need. Remember, like we talked about in class, right? So I want to solve for the capacitor voltage, which means that I need an initial condition not just for the voltage, but I also need one for the derivative of the voltage. So in other words, in my step 2, I need to find dVc dt of 0 plus, right? Which is basically IC of 0 plus divided by C. Okay? So really what I need to find here is IC of 0 plus. Okay? All right, so now as we kind of described, to be able to figure this out, the critical thing to remember is we know that the voltage on the capacitor always has to be continuous and the current in the inductor always has to be continuous. If the voltage on the capacitor has to be continuous, that means that over a very short time period, if I only analyze the circuit for a very short time period, I can think of the capacitor, the capacitor as a voltage source, right? In other words, if these, so when I say a very short time period, basically from right before 0 to right after 0, that guy acts like he's a constant voltage source stuck at 12 volts. And so what I do is I redraw the circuit assuming that's the case. Now, similarly for an inductor, for an L, the current in the inductor is constrained to a particular value over a short time. So that means that it looks sort of like a current source. Okay. So the way that I draw that is I say, okay, well, I need to draw in the circuit as it should be represented. And so the way I do that is if I go back, okay, here was the original circuit. I'm going to redraw that circuit now, saying that, right, so at t equal to 0, I basically have my 12 volts, got my 4 ohms, I have a current source, okay, I got my 2 ohms, and I have this guy. Now here, Vc of 0 plus is how I'm going to represent this guy. He's going to be 12 volts. The inductor has a voltage across it, VL, and the current through here is, in this case, 0 amps. The current source was 0 amps. Now that's just what's happened in this problem. If the situation was different in a different problem, it might be that that was a 1 amp source or a 10 amp source or whatever the problem dictates it to be. It basically tells me that that current there is 0 amps. All right, now, a couple of things that I got to remember. If I'm talking about I sub C, I need to think about directionality on that current. And that's something that, we didn't really define here at the beginning, but I should define it now and say that I'm going to call that IC. Now I say I need to define that now because I'm going to make an important statement here. At the beginning of the problem, you define the definition of the directions of the currents and the voltages, and that does not change as you go through the problem. All right, so if you have multiple different steps that you go through, like if you're doing superposition or something like that, you do not change the directions of the currents and the directions of the voltages. They need to stay consistent throughout the entire problem, okay? All right, so that's important because that means that here, I sub C of 0 plus is going that way. All right, now, quick thing to remember, if I talk about a voltage source, we talked about this in class, if I talk about a voltage source knows its voltage, but the current through that voltage source is determined by everything else in the circuit, okay? Similarly, for a current source, the current is determined, but the voltage is determined by whatever the rest of the circuit tells the voltage to be, okay? So let's see what that means here. All right, so to figure out what I sub c of 0 plus is, right, well, I know the current in this branch is fixed at 0. I know the current here actually is fixed at 12 divided by 2 ohms. So let me do a KCL. I'm just going to call that I right there. So I have by KCL, I have 0 amps, or what I'll call IL of 0 plus, is equal to I plus I sub c of 0 plus. Okay. Looking at this, that means that 0 equals, so what is I? Well, I would be Vc of 0 plus divided by 2. All right, because we know that Vc of 0 plus is 12, that means I have 6 plus Ic of 0 plus. Or I have Ic of 0 plus equal to minus 6 amps. Okay, like that. All right. So at this point, again, what I'm going to need ultimately in the end is I'm going to need to know dVc by dt at 0 plus. So because I know I equals c dv dt, I know that dVc dt at 0 plus equals Ic of 0 plus divided by c. So that gives me minus 6. In this case, c, if I go back to the beginning, is actually a half. So that makes this minus 12. Now, what's the units on that guy? Numbers are useless without units. Although the unit is somewhat strange, it is minus 12 volts per second. In other words, it's telling me the rate at which the voltage is changing. Okay? All right. So at this point, as I've gone through my step 1 and 2 here, again, these are different than step 1 and 2 in the book. All right? But I need to do these anyway, all right? They tell me essentially what the initial conditions are going to be. Now the other thing I'm going to need to get in this case, what I'm going to call my step 3, is to find V sub c steady state. Okay? In other words, I want to find what the steady state condition is. Now again, once I write my differential equation, which is going to be what I do next, right? I could do the math way to figure out the steady state, but I prefer to use the sort of the physics route. So sort of look at the circuit and see what's happening. All right, so in steady state, what I know, so steady state means as t goes to infinity, what I know is that all the d by dt terms always go to 0. In other words, everything in the circuit becomes constant. All the voltages, all the currents become constant. All right, so I just need to look at what the inductor and capacitor do. So basically what I know is if the if the inductor current has become constant, I know the voltage across it's 0, and if the capacitor voltage has become constant, I know that its current is 0. So if the current in the capacitor is 0, it's an open. If the voltage here is 0, it's a short, right? So I know the inductor is a short, I know the capacitor is an open. So if this switch is closed, then at time t equal to infinity, what I have is just simply a voltage divider consisting of my 4 ohm R1 and my 2 ohm R2. Okay? So in other words, my steady state circuit is simply 12 volts, 4 ohms, 2 ohms, like that. And because there's no current in that capacitor, I don't need to even worry about it. So I can say, oh, not Vz of 0. Careful. There we go. Okay. Let's call this VC steady state. So VC at infinity. So if I look at this, okay, again, it's a voltage divider, so this is pretty straightforward for me to figure this out. So if it's a voltage divider, I have 2 over 4 plus 2, 6 times 12. So that puts that at 4 volts. Okay. So now I know everything I need to get the initial conditions and the final value. So I know the steady state voltage. So when all is said and done, long after the switch is closed, the voltage on here is going to be 4 volts, and it's going to begin at 12 volts. And I know that the current is initially such that this capacitor is discharging. Okay, so that's important. Just because this capacitor current is defined going this way, I know that initially, at least, at time t equal to 0, the current is going to be outward. It kind of makes sense because this guy starts at 12 volts and he's going to end at 4, which means that charge has to leave, which means the current's probably going to flow out rather than in. All right, but again, important to keep the current consistent throughout. All right, so now I'm going to go to basically what I call my step 4, which is really the book's step 1, which is to write the differential equation. Okay, in this case for V sub c. All right, so let's draw the circuit, and I'm going to do this. I'm going to do this in terms of component values here. All right, and there's R2. There's C and V sub C. So again, I need to be careful about all my directions. So I've defined IC to be that way. I defined I to be that way. I defined IL to be that way. And now I've got VR and VL defined that way. Again, I need to always be careful about all my signs and directions. All right. Now, to write this differential equation, basically I'm going to have to do some KCL and KVL analysis. So first of all, let's write what we know. So by KCL, at the one node that I have, the only node that I have IL equals I plus IC. Okay. So if IL equals I plus IC, the one thing that I kind of clearly know from that is I is, so the current in the middle R2 there is basically whatever the capacitor voltage is divided by R2, and IC is simply C dVc by dt. Okay. Now by KVL, now where am I going to apply KVL? KVL I'm going to apply around this loop here. All right. Again, I'm always very slow with my KVLs, right? So I do this as 0 equals minus 12. So I start in this corner and I go up, right? So I always kind of work in that direction. So I guess it's sort of a clockwise direction. All right. So when I do that, I end up getting minus 12 plus the voltage across the resistor. So that is IL R1 plus VL plus the voltage across the resistor, which is simply V sub C. Okay, so that tells me that 12 equals IL R1 plus V equals L dIL by dt plus v sub c. So at this point I have two equations and two unknowns. What do I need to do? Well, basically I need to substitute into this equation. So I substitute IL into this equation. All right, so when I do that, I'm going to get a long and kind of ugly equation, I think, from that whole process, right? So I'm going to get 12 equals R1 times IL. So IL was VC over R2 plus C dVC by dt. Okay. Plus L times d by dt of VC over R2 plus C dVC dt plus VC. Okay. So R1 over R2, I'm going to simplify that a little bit here. So VC plus R1C dVC dt plus L over R dVC dt, like that, plus LC. Here's where the second derivative comes in, right? I've got derivative of a derivative plus VC, like that. All right, now at this point, yeah, you could simplify this, symbolically like this. I don't want to. It's going to get messy and ugly. It already is messy and ugly. So at this point, I go ahead and I plug in all my numbers. So if I have R1 equal to 4 ohms, R2 equal to 2 ohms, I have C equal to 1/2 of a farad, and I have L equal to 1 Henry, way back here. Okay, 1 Henry, 1/2 a farad, 2 ohms, 4 ohms. All right, I go ahead and I plug in all those numbers, and I end up with 24 equal to d squared, well, in fact, yeah, d squared dvc dt plus 5 dvc dt plus 6 vc, like that. All right, that is ultimately what I end up with when I write down this particular equation. So if, and again, one thing to note is I put this into that sort of standard form, right, which is to say that this is d squared vc dt squared plus 2 zeta omega naught dvc dt plus omega naught squared v sub c. Okay, so I can see right away omega naught squared equals 6, and I see that 2 zeta omega naught equals 5. Okay, if I plug that in here, okay, and go through and solve that guy, what I find is that my zeta is something like 1.02 something, right? Which tells me, remember, my zeta is greater than 1. That tells me I'm basically in my overdamped case. Okay. If I'm in my overdamped case, that tells me that my transient solution, this way, V sub C transient. Okay, so I should be a little bit careful now. In terms of the steps that the book defined, I guess, right? I'm sort of starting to skip around in my steps. I'm starting to merge them and blend them. Okay. So just to be clear, let me say, so what I guess, okay, I was calling this my step 4, which is the book's step 1. I guess what I started to do as I went in through here, right, the characteristic equation, so I guess I should say step 5, or the book's step 2, is to say that from that differential equation that we just wrote, I have s squared plus 5s plus 6 equals 0. All right. So at that point, I write my differential equation. All right. And then effectively, what I then do is my what I'm going to call step 6, or step 3 in the book. All right, which is basically to try to figure out whether the system is overdamped or underdamped. In this particular case, I look at the coefficients I've got. That means that my system is overdamped. All right, so if I'm overdamped, all right, cramming too much stuff in here. If I'm overdamped like this, all right, in the overdamped case, now I need to figure out what the transient response is actually going to look like. All right, so what is my transient response going to look like? So what is going to be, in my case, step 7, which is step 4 in the book, is basically to write the transient response. So V sub C transient is, in this case, since it's overdamped, it's the one with the 2 distinct exponentials. So basically A1 e to the S1t plus A2 e to the S2t. And so if I solve the differential equation to figure out my S1, or sorry, the characteristic equation to figure out my S1 and S2 are, in this particular case, I would find that my S1 is minus 2, and my S2 is minus 3. Okay? So not too hard to kind of go through that. Now, that tells me that the transient response is A1 e to the minus 2t plus A2 e to the minus 3t. Okay? Now, that basically tells me now that my total response, V sub C, which is V sub C steady state, plus V sub C transient, is, I have to go back, what was V sub C steady state? We determined that back here in step 3. That was 4 volts. All right, so 4 volts plus A1 e to the minus 2t plus A2 e to the minus 3t, like that. Okay. So now what I need to do is move into my step 8, or I guess what is step 5 in the book. Which is basically to determine those 2 unknowns, A1 and A2. And I determine those using, the stuff that we figured out earlier. In other words, I can say VC of 0 plus, okay, I determined that way back when to be 12 volts. And I know that has to equal 4 plus A1 plus A2. Why do I know that? Because if I go back to my original equation here, and I plug in t equal to 0, I get just A1 for this term here, and just A2 for this term right here. All right, so that's one equation. So this guy becomes basically 8 equal to A1 plus A2. All right. And the other equation is for the derivative, okay? So in this case, I know that that derivative, we figured that out back here earlier on. All right, dvc dt of 0 plus was minus 12. Okay, so I get this as minus 12. Now that has to equal the derivative of this guy. So if I take the derivative of a constant, that's 0. All right, so the first term gives me a derivative of 0, and then these guys I get minus 2a1 e to the 0 plus minus 3 a2 times e to the 0. Okay, so that tells me that I have, ultimately I've got minus signs around, so I basically have 12 equals a1. Be careful about that. 12 equals 2a1 plus 3a2. So I see that I've got one equation, two equations, and two unknowns. You can combine those and you basically end up with a1 equals 12 and a2 equals minus 4, which tells me that v sub c of t is 4 plus 12 e to the minus 2t minus 4 e to the minus 3t. Okay. All right. And that is the final answer that we get after all of this. All right. Now, if I just do a quick check on some things here, I can see some important factors. I should be able to see some important factors from all of this. Clearly, the final value of the voltage is 4 volts, right? Clearly, that's equal to 4 volts. If I want to check, right? So as t goes to infinity, each of the two exponentials go to 0. At time t equal to 0, I have 4 plus 12 minus 4, which is going to be equal to 12, right? So it matches my initial conditions, all right? Now, if I looked at what this looks like, all right, I'll give you some example MATLAB code that you could take a look at to see how it evolves as a function of time. But it sort of tells me what that response ultimately looks like. All right, so hopefully that helps to sort of understand that problem a little bit better. This is pretty similar to, if I look in your homework here. So a problem, like this particular problem, right? I sort of follow the same sort of process, figuring out what's happening at time t equal to 0 plus, okay? Writing the capacitor voltage, determining it's over or under damped, and then trying to figure out how the capacitor voltage evolves as a function of time. That's really those last couple of steps. And again, I have to look at what's happening at t equal to 0 minus and t equal to 0 plus, get all those initial conditions. Very similar to what you're doing, okay? All right, that's that.